In this lesson, we're going to be working with co-function identities. Now, the co-function identities are in fact identities that relate the trigonometric lines of pi over 2 plus or minus theta to the trigonometric lines of theta. It's in fact similar to the work that we did in a previous lesson on with the associated arcs or the symmetric formulas, which were in fact similar identities that do relate the trigonometric lines of negative alpha and the trigonometric lines of pi plus or minus alpha to the trigonometric lines of alpha. So in fact, they're similar identities, except that over here we were working with negative alpha or 2 pi minus alpha, and over here with pi plus or minus alpha. However, the co-function identities do relate the trigonometric lines of pi over 2 plus or minus theta to the trigonometric lines of theta. Now, before we put these into examples, we're going to go through them first and justify them on why these identities do make sense. Now, over here, if we start with the trigonometric lines of pi over 2 minus theta. So first, starting with cosine of pi over 2 minus theta, the identity says that it's equals to sine theta. And sine of pi over 2 minus theta is cosine theta, and tan of pi over 2 minus theta is cotan theta. Now, over here, if we were to make sense of these identities on the unit circle, so if I'm starting here with point P, where OP is forming the angle theta with the horizontal axis. Now, over here, if this is the measure of angle theta, then by subtracting theta from the vertical axis, since we're subtracting theta from pi over 2, so subtracting theta from pi over 2, then this angle would in fact be, this whole angle, let me just fix that. So this whole angle would in fact be pi over 2 minus theta. So from pi over 2, I'm actually subtracting theta. Now, by comparing the trigonometric lines, now if this is the point P forming an angle of theta with the horizontal axis, and we have a point P prime here forming an angle of pi over 2 minus theta with the horizontal axis. Now, we do know that sine and cosine are in fact the coordinates of the points on the circle forming that specific angle. So here the horizontal axis is the axis of cosine, the vertical axis is the axis of sine. So to look for cosine of an angle, we do in fact look for its abscissa. So by comparing these two triangles, you'd notice that these two right triangles are in fact similar. However, having here the abscissa of the point P. Now, what I just highlighted in red is in fact the abscissa of the point P. So the abscissa of the point P, which is in fact cosine of theta, is in fact equals to the ordinate of point P prime. The ordinate of point P prime is in fact defined by sine of that corresponding angle, which is pi over 2 minus theta. So this is where this identity in fact comes from. It's sine of pi over 2 minus theta equals to cosine of theta. Similarly here, since over here you'd notice that this is sine of theta, since this defines the ordinate of point P, the y value of point P. So in fact, over here, you'd notice that it's equals to cosine of pi over 2 minus theta, defined by the abscissa of point P prime. So this is why cosine of pi over 2 minus theta is in fact equals to sine of theta. Okay, and over here regarding tan, it's in fact by definition. Tan of pi over 2 minus theta is in fact sine of pi over 2 minus theta divided by cosine of pi over 2 minus theta, which leads to cosine over sine, which is in fact cotan. Okay, so Over here, it's similar for pi over 2 plus theta. So if this is pi over 2 and I do add the same angle to it, so if I add a theta to pi over 2, that would in fact leave me with point P double prime, what I called P double prime here. So you'd notice here that in fact more or less we have a right triangle with similar dimensions. So over here you'd notice that we do have x of, let me just highlight that in red since it was highlighted in red there. So you'd notice that the abscissa of P defined by cosine theta is in fact the ordinate of point P prime. It's the same. And over here in quadrant 2, sine is positive. So you'd notice that this is in fact angle pi over 2 plus theta. And you'd notice that its ordinate, the ordinate of the corresponding point is in fact equals to the abscissa of point P, so which leaves me with cosine of theta equals to sine of pi over 2 plus theta. And similarly for the abscissa, you'd notice that this side of the triangle has the same side of that triangle, so they have the same length. However, this one is positive while this one is negative. So this is why sine of theta, this is what defines sine theta, is in fact equals to negative cosine of pi over 2 plus theta, since it's the abscissa. So cosine of pi over 2 plus theta, I repeat, is in fact the abscissa of point P double prime, okay, which you'd notice it's the opposite of sine of theta. Okay, so and similarly for tan, it's by definition of tan being the ratio of sine and cosine. You'd notice that leaves me with negative cotan theta. Now, of course, in order not to confuse these identities, the same way we used to determine the correct sign of the functions for the identities with negative alpha and pi plus or minus alpha, we can also apply that small trick here. However, just keep in mind that with pi over 2, cosine in fact is equals to sine of angle theta. The trigonometric functions may seem like they're switching more or less. So over here, for example, if I wanted to find sine of pi over 2 plus theta. Now, I know for a fact that with pi over 2, the sine becomes a cosine of theta. I just need to determine if this is positive or negative. Similarly, for pi over 2 plus theta is in quadrant 2, and I look for the sign relative to the original function. The original function is sine, so that is positive, so I know for a fact that this is a positive cosine. You could use this trick in order not to confuse the identities and be able to apply them properly. Okay, now let's just have a small example here. We are given cosine x to be equals to 1/3, where x is an acute angle, so we know for a fact that x is in the first quadrant. And find the exact value of cosine 5 pi plus x, sine of 9 pi over 2 minus x, and cosine of 7 pi over 2 minus x. So you notice here that we do need to apply these transformation formulas, whether the cofunction identities with pi over 2, the ones we just saw, or over here the associated arcs with pi plus or minus alpha. So over here, let's just start with the first one as a quick recall on the previous lesson. So we know that the associated arcs are those in terms of negative alpha and pi plus or minus alpha. However, you notice here that I have a 5 pi. I do not have a 1 times pi. So, but that can be fixed because we do know that cosine is pi periodic, and I know for a fact that 5 pi can be seen as 4 pi plus pi. So over here, 4 pi being a multiple of 2 pi, in fact, can be disregarded because we do know that cosine of x is in fact equals to cosine of x plus any multiple of pi, any multiple of 2 pi. So as we keep on adding full turns to the angle, the position on the unit circle is the same. These two angles do have the same cosine since they have the same abscissa. So over here we can consider that this is equals to cosine of pi plus x. So now we apply the symmetric formula for cosine with pi plus x. So I need to locate the angle here in order to determine the correct sign. So we have pi plus x, that's in quadrant 3. In quadrant 3, cosine is negative, so that is negative cosine x. I remind you here that the pi is not really vanishing anywhere. What we're saying here is that pi plus x and x have opposite cosines. However, we do use this trick in order to determine the correct sign in the identity in order not to confuse them anyway. So it's negative cosine x, and we do know that cosine x is 1/3, so cosine of 5 pi plus x is in fact negative 1/3. Now similarly here we have sine of 9 pi over 2 minus x, and we need to determine the exact value to that. So 9 pi over 2 minus x. Again, the co-function identities are in fact pi over 2 plus or minus x or alpha, whatever. Okay, so however, I do have here 9 times pi over 2, so I need to bring this back in terms of one of these angles, pi over 2 plus or minus x. So over here, by looking at 9 pi over 2, we do know that 9 pi over 2 is in fact 8 pi over 2 plus pi over 2, and 8 pi over 2 is 4 pi. Which is also a full turn. It's a multiple of full turns. It's in fact 2 full turns because every full turn is 2 pi. So over here we can disregard the 4 pi since we have sine to be 2 pi periodic. So we know that after 2 full turns, the trigonometric line or the value of sine will in fact repeat. So that is sine of pi over 2 minus x. So over here, by looking at this identity, this is in fact a co-function identity. It's pi over 2 minus x. So again, I do locate that angle in its proper quadrant in order to determine the correct sign in the transformation. So pi over 2 minus x, pi over 2 is the 90 degrees in fact, minus x, we go back to quadrant 1. So in quadrant 1, all trigonometric ratios are positive, so sine is positive. However, keep in mind that the pi over 2 switches the sign into a cosine, so that that is in fact cosine of x, which is 1/3 according to our given here. Now moving to the last one, I have cosine to be 7 pi over 2 minus x. Now looking at this angle here, it is in terms of pi over 2, so I might be using the co-function identities. However, I do have a 7 times pi over 2 and not exactly a pi over 2, so I need to bring that back into pi over 2. However, if I were to do the same thing I did for the previous one, what I did is split 9 pi over 2 into 8 pi over 2 plus pi over 2, where 8 pi over 2 is in fact 4 pi, which is a multiple of 2 pi, which helps me eliminate or disregard these number of full turns. However, if I were to do the same thing here, if I were to go for 6 pi over 2, for example, if I were to go with 6 pi over 2 plus pi over 2, the 6 pi over 2 is in fact 3 pi. That is not a multiple of 2 pi. This does not give me 2 complete full turns. So for that reason, I cannot use the 6 pi over 2. I cannot use this combination for a reason that I cannot disregard the 3 pi inside cosine, because cosine is 2 pi periodic. It is not pi periodic. If this were to be a tan, then I could use the 3 pi because tan is pi periodic. However, cosine and sine are not pi periodic, so I have to find or to remove full terms. So instead of using this combination that does not really work, what I could do is again go for the 8 pi over 2. Okay, so I could go for the 8 pi over 2. Now, there are two possible ways here. We're going to tackle both of them. So we could go for the 8 pi over 2 and consider 7 pi over 2 to be 8 pi over 2 minus pi over 2. So in that case, that would leave me with cosine of 4 pi minus pi over 2 minus x, and the 4 pi can be disregarded as it is a multiple of 2 pi inside cosine, and cosine is 2 pi periodic, which leaves me with cosine of pi over 2, negative pi over 2 minus x. Now I still need to, I still did not reach my cofunction identity, because my cofunction identity is a pi over 2, not a negative pi over 2. So in order to get to pi over 2, what I would do here is factor out the negative. So it's cosine of negative into pi over 2 plus x. Now you'd notice here that this became in the form cosine of negative alpha. So if I were to call this alpha, we'd know that cosine of negative alpha, according to the associated arcs, is in fact cosine alpha, because negative alpha is in quadrant 4, and in quadrant 4 cosine is positive. So that is a cosine alpha. So which in fact leaves me with cosine of pi over 2 plus x, which leaves me with cosine alpha, or I called alpha pi over 2 plus x. So we did it here over 2 steps. Now that we've reached the cofunction identity, we can in fact apply it. Pi over 2 plus x is again in quadrant 2, but in quadrant 2 cosine is negative, so that's a negative here. And with pi over 2, the trigonometric function switches, so we do have here that cosine of pi over 2 plus x is in fact a negative sign. However, I do not have sine given. I have cosine, but I can find it. I can find it using the Pythagorean identity that relates sine and cosine. Cosine squared plus sine squared equals to 1. So I can find sine using cosine, in fact. But here what matters is this process that actually led cosine of 7 pi over 2 minus x to be equals to negative sine x. Now there is another way to actually do that. Before we actually find sine, let's just go for method 2. So in method 2, what we would in fact do is, what was it again? It's cosine 7 pi over 2 minus x. Now over here, my cofunction identities go for pi over 2 plus or minus x or alpha, whatever. Okay, however, keep in mind that since 3 pi over 2 is in fact negative pi over 2, over here you'd notice that in the previous slide here, we got to a point where we had negative pi over 2 here, and we do know that negative pi over 2 is the principal measure of 3 pi over 2. We do know that this is 3 pi over 2 if we're in fact moving on the circle in the positive sense. or negative pi over 2 if we're moving in the circle in the negative sense. So negative pi over 2 being the principal measure of 3 pi over 2, what we could have done here is replace negative pi over 2 by 3 pi over 2. Now, why is that useful? Because the cofunction identities work the same way with 3 pi over 2, but instead of working with quadrants 1 and 2, would be working with quadrants 3 and 4. So instead of doing pi over 2 minus theta or pi over 2 plus theta, what we'd be doing is 3 pi over 2 minus theta, or 3 pi over 2 plus theta in quadrant 4, and you'd in fact look for the signs similarly to how we did it with the cofunctions identities with pi over 2. So over here, what you could have done, in fact, instead of going all the way to 8 pi over 2 minus pi over 2, what we could have done is aim for 3 pi over 2. So consider 4 pi, I'm sorry, I forgot to write the cosine here. So consider that 7 pi over 2 is in fact 4 pi over 2 plus 3 pi over 2 minus x. 4 pi over 2 is in fact a 2 pi, which is a full term. It can be disregarded inside cosine. So that leaves me with cosine of 3 pi over 2 minus x. And 3 pi over 2 minus x, looking at it on the unit circle, this is 3 pi over 2 minus x. We'll get back to quadrant 3. So in quadrant 3, cosine is in fact negative. So this is equal to a negative. And don't forget that whether it's pi over 2 or 3 pi over 2, the trigonometric functions switch. So cosine does in fact switch into a sine. So we notice that we were able to reach the negative sign way quicker than aiming for full turns here with the principal measure. Okay, so sometimes it might be easier for you to aim for 3 pi over 2 instead of pi over 2. The process could be shorter, in fact, the same way you've seen here, and the cofunctions identities with 3 pi over 2 would in fact work similarly to those with pi over 2. So now to wrap up this example, let's just find sine. We know that sine squared, that's an x here, it's not a theta, so sine squared is 1 minus cosine squared, and we know that cosine is given to be 1/3, so it's 1 out of 9, which is in fact 8 out of 9. So sine x is in fact 2 square root 2 over 3, or negative 2 square root 2 over 3. Now, what do we know about x here? We know that x is an acute angle. An acute angle is in fact located in quadrant 1. In quadrant 1, all trigonometric ratios are positive. So this is in fact rejected. So since sine x is 2 square root 2 over 3, and we've just found that cosine of 7 pi over 2 minus x is negative sine, so in fact that would be negative 2 square root 2 over 3.